be like. Okay, I talked a long time. But maybe you might remember that time delay distances with strong lenses are interesting because they're accurate, but they're also independent. And so they can contribute to this sort of global inference of what dark energy might be like. We saw that B1608 and RHJ1131 each provide comparable constraints on the Hubble constant to other probes right now. And we saw that a stage 4 dark energy experiment in the 2020s will need 100 to 1,000 lenses, as well measured as B1608. We saw that the surveys that are going on right now would find enough lenses. The problem is in monitoring them. So we'll be able to monitor some of them, but not all of them, and we'll do the best we can. But with LSST, we should be able to monitor 3,000 of these things, and then select the 1,000 that might work best, and then follow up as many as we can. Measure many, many time delay distances. And then lastly, we have to keep in mind that this model we have for understanding our data, we have to keep up with the precision. As we have more and more lenses, we get more and more power to measure distance. But we also get more and more susceptible to systematic errors. And so what we're doing between now and 2020 is trying to identify all the things that can go wrong and try and solve them before we get there. Okay, thank you very much.
Thanks a lot for the interesting talk.
May I ask 2 questions?
Okay, question number 1. How long will it take to get these 100, let's say 100 lenses from LSST, assuming starting its operations in 2020? How long will it take to get to your previous page results?
Okay, good question. We'll start seeing these strong lenses in the LSST images almost straight away. The easy ones will pop out if we're well set up. In order to measure time delays, we know that we need at least 3 seasons in order not to be confused by particular features in the light curve. And so 5 years would be better. And so that's when the precise time delays will start coming in. But before then, we could start following up the systems that we predict will be good for cosmography. That is, lenses that are in nice environments, that have nice sightlines, or that have promising-looking image configurations with lots of information for the lens modeling. So I think we can spread out the follow-up observing over several years, and then the time delays will catch up.
So that would be pretty much competitive in terms of timing against JDAMs? The 0.2 for W0 and 0.7 for WA?
Yeah, because the other experiments need both things like weak lensing and BAO. They need a large amount of sky, but they also need depth. And it will take time for LSST to build up the depth. And so I think we'll see each of the cosmological distance measurement methods advancing sort of similarly through the decade.
My question number 2, sorry, is about this this red remark. Presumably, you can eventually go more into not 100 lenses, but 1,000 or 3,000. So when are you going to hit the wall in terms of the dark energy accuracy or precision determination?
We don't know yet. So the reason for investigating the systematics now is to answer exactly that question. I suppose we are optimistic about the potential for strong lenses, but we have to do these investigations about the line of sight, how well we can measure lenses, in order to understand what our sort of systematic limit is. What's the fundamental limit? And we don't yet know where that is. It's still a relatively young way of measuring distance in the universe, and so we have to do these investigations. But we have some time before LSST, and we're learning by doing distance measurements with surveys like DES and also hopefully with HST.
Question number 3. What's the most significant systematic error?
At the what, sorry?
The systematic error.
At the moment, it depends which lens.
I'm just curious that, for example, even single lensing, okay? So what limit is enforced you have about 20%?
Right.
or any room to improve?
I think for B1608, which is on an overdense line of sight, I think it's probably our understanding of the mass distribution along the line of sight, so modeling all these weak lensing effects. But for other lenses that are in underdense lines of sight, I think then the systematic error at the moment that dominates will be how well we can constrain the lens model itself. And so one of the things that Sherry's group is working on is trying to understand the systematic errors that come in when you model lenses. And at the moment, with the 2 lenses, 5 lenses, the systematic error is less than the statistical error. But as we go to bigger samples, we'll have to get better and better at lens modeling. Now, one reason why I'm excited about the IFU spectrographs, that is the instruments that take images at many wavelengths, is that you have all of those different images to help you understand the lens. So there's more information about the Einstein ring, better constraints on the lens model. And so I think with those we should be able to go one step further and reduce that systematic error so that we can use hundreds of lenses to do this. But again, we have to do those experiments with simulated IFU data to make sure we know what we're doing.
You emphasize that after LSC finds these lenses, there needs to be a lot of follow-up work. Most of the follow-up work you described came from ground-based telescope. Are there any advantages to having a dedicated space mission, like some version of cosmological Kepler? In which case, you need to plan for such a mission now.
Yeah. So Leonidas Moustakis at JPL has been thinking about and proposing for just such a space mission. It's called the Omega Project. And his idea is to make a dedicated space telescope, quite small, but big enough that you can do very accurate monitoring in time, but also high resolution imaging of the rings. So that's one possible route for doing the follow-up.
What's the price?
But right, exactly, at a price. So I suppose I come from a thrifty background, so I'm thinking about facilities that are already planned for other reasons. What could we do with them? And it does seem as though the IFUs on planned extremely large telescopes like TMT or GMT, EELT in Europe, they look as though they could be very well matched to what we need. That is, making a high signal to noise, high resolution image, many different wavelengths. We can measure the redshifts of the lens and the source. Maybe we measure the velocities of stars in the lens galaxy. And then also make a very clean image of the Einstein ring and use that in the model. So I'm very optimistic about that. Tommaso Treo is also looking into the JWST possibilities. He's very excited about doing the same kind of observation there. IFUs in working in the infrared from space should also be very good for this kind of follow-up. And if we can follow up these large numbers of lenses and make these kinds of measurements, it's nice because the dark energy, the distance measurement is almost, I'd say, almost the hardest thing to do with these systems. There are other things you can learn, many things you can learn about the mass distribution of massive galaxies from the same data set. You can look for little perturbations to the rings, to look for small-scale mass structures that you wouldn't otherwise be able to see. You can look at the evolution of galaxies in great detail in their mass. So there's lots of science we could do with a legacy data set like this from an IFU survey with an ELT or a JWST.
I would think that the top prize is to find W is equal to -1 at all Z, right?
I don't mind what we find. I'm just interested to see what comes up.
Other
Or not to
questions?
find it.
Yeah.
Other questions or questions from students?
Is it potentially capable of detecting the anisotropy of dark energy across the space?
Ooh, that's a good question. Okay, so with so many lenses, it's true. We could look at do the time delay distances over here look different from the time delay distances over here? We can't do there because LSST doesn't look in the north. We could do there to there. And I think that sort of experiment would be very interesting to do. You can do it with supernovae as well. And in fact, I think all of the distance probes. And having such a wide survey and such high statistical power will enable that kind of experiment in a way that hasn't been done before. So that's a great opportunity, yeah.
Other questions? I'm curious, are there other experiments that show error contours that's perpendicular to what you have done?
Okay, so let's go back here. So it turns out that, roughly speaking, they all have very similar orientations to this one. There's a little bit of variation that's enough to break the degeneracy a little bit and improve the constraints. But roughly speaking, they're all sort of similar. Although I think one is different. I think and you have to check me because I'm not sure about this, but I think if you look at the direct measurements of the expansion rate with these extremely large telescopes, that's looking for the change in a galaxy's redshift
Percentage
with time. So you measure the redshift at 2020, and then you come back 10 years later, and it's a very slightly different redshift because the universe has expanded within those 10 years. I think that gives you a slightly different, or a significantly different angle here. So that's a good one to watch out for that reason.
This is not a question, just a comment. I remember that Albrecht's group, as well as the decadal survey, recommend that since the current accuracy was like for the omega W0 about 10% and WA 100%, and the expectation or the wish is that in a decade or so to reduce it down to 0.2 or 3 for W0 and about 10% for WA. So I see this very exciting that the LSST is promised to deliver that. Yes.
Okay, if there is no further questions, let's thank the speaker. Students are welcome to talk to Phil in person.